And then thank you for the invitation. It's really happy to come to Trieste. This is our first visit for this, so then it's really fantastic. Okay, so then today I'm going to talk about some geometric representation theory and this QQ character. So okay, and which is based on a couple of the joint work is this Go Noshita and Vasily Pestin. And first of all, okay, I'm going to talk about this. What is this QQ character? I suspect that this is not, very famous enough for this in the audience. But actually, this is more or less my talk is aim of my talk is that okay, this is more or less subject to this some representation theory in the context in the connection with the geometry. But actually, this technology here is really developed in the context of gauge theory, especially this instanton counting or something like this. And actually, this talk is also really motivated by this instanton counting stuff. Okay. So then, okay, first of all, I'm going to tell you what is this QQ character. So basically, so as this name suggests, so this is a kind of the two-parameter deformation of character of, for example, Lie group or Lie algebra. And then actually this QQ is okay, if you know familiar with instanton counting, these two Q parameters are related to this so-called omega background parameters in this sense. Okay, so then let me use. Okay, so then in order to demonstrate what's this, so let me explain. Okay, bit really two pedagogical thing, but let's start with some what is a standard character, then how to deform this. Okay, let us give you several examples, and then I will give you some construction. The first, let's start with this, for example, M of W, so which is a one-dimensional SL2 module. So this is well known. So SL2 algebra is very simple enough, and then this is okay. Okay, more precisely, this is a W plus one-dimensional finite dimensional module of representation SL2. And actually, so okay, so then we have this. And if you want, in the context, in a physical terminology, W is 2 times spin, if you want. Okay, so then we have this kind of representation module. So then standard character associated to this module is very simply, okay, given like this. Okay, so this y of 2w, w minus 2, plus w minus w. So in total, you have w plus 1 term. So then that's why, so this is related to this w plus one-dimensional module. So this, my notation is, okay, this compatible. Okay, so the leading power is now w. So this is my preferred notation. So that's why I'm now using this kind of notation here. Okay, so using this character, okay, so then in that sense, this y is related to some weight information, etc. And okay, so using this character, so we can discuss a lot of very important behavior and, for example, representation, okay, tensor product, decomposition, etc. It's a really nice toolkit to compute this kind of behavior. Okay, so this is a standard character, but then let me think about a bit of deformation of this stuff. Okay, now first we think about a bit the deformation of this module. So this is similarly that is one-dimensional module, but it's a module of the deformed algebra, which is so there's a quantum affine algebra SL2. So even okay, we have a bit of deformed version situation. As far as concerning, so there's, for example, finite dimensional representation. So we have an almost similar structure. So then, now we have an extra parameter x associated to this module. So this is now in this context called a spectral parameter, and this parameter plays a very important role to realize a representation of this affine algebra. Okay, correspondingly, so we can think about okay, say let's call character associated to this okay module with this one parameter deformation. So then, okay, so, okay, let's think about the simplest example, the w equals 1. So just a two-dimensional representation. So in this case, we have this kind of character here. So now, correspondingly, we have a spectral parameter dependence. So then correspondingly, this y part, so this is...
For q equals to 1, y It should not be twice. Y minus 1, I think, or something.
Yeah, sure. Yes. Sorry. Yes. Yes. Sorry. Yes. Yeah, I always forget this kind of. Okay, but yeah.
Two jumps simultaneously.
Yeah, sure. Yes. Y plus 1 over Y. Exactly. Yes. So thank you for this. Yeah. Anyway, so please interrupt me anytime if you have any question and so on. So then, okay. So then the point here is that now we have spectral parameter dependence. So this Y is now promoted to the function in this sense. And then we have a shift with respect to this quantum parameter. And this is called so-called a Q character, which is introduced by the Knight, and also this Frenkel-Reshettin. Yes, and this is actually, so Knight, this was in the context of Yang, kind of the cousin of this quantum affine algebra. Frenkel-Reshettin introduced a Q character for this quantum affine algebra. And one thing, okay, so this is one parameter deformation of this. And then we can, okay, so now this Q is, okay, now we have one parameter deformation. And of course, you can realize that if you take Q to 1, so this is going back to the, so just the same function. So then we have a basically reduction. So then QQ character here is, okay, so let me write, okay, maybe it's better to write this. QQ character is similarly defined for this quantum affine algebra. So then we have, okay, 1 over y x of q1, 2 inverse here. And then the notation here is that now q1, 2 is now just product of two q parameters. I'm not sure, so maybe this side. Okay, I will write large as much possible. Okay. Two parameters, yes.
But it depends only on their product.
So yes. So it did, yes. Yeah, in this case, so actually there's no crucial difference to this Q character, but if you think about the tensor product, etc., so we have, significant change. So it's a really point here. Okay, so in that sense, okay, so then, sorry, this is again for this two-dimensional module here. Yes, and this is a QQ character introduced by Nekrasov. So the original, his motivation to introduce QQ character is that, okay, for example, as this name suggests, for example, you have Q1, Q2 parameters. So that this, as I said, this corresponds to the omega background parameter in the four-dimensional instanton counting. And then, so this QQ character is a nice tool to describe the so-called non-perturbative Schwinger-Dyson equation, etc. Okay. So anyway, so this has a really gauge theory origin. Okay. So then I want to discuss. So then I think it's nice to explain what is a difference between QQ character and the Q character. As I said, so this just a two-dimensional module, so no crucial difference. But if you think about the tensor product of this, for example, 1x, so we have a significant difference. So in this case, standard character and the Q character. So this tensor product of character is again just a product of characters. But in this case, so we have a bit difference. For example, we have x, basically product of this, but we have additional structure actually. So x prime q1, 2. X inverse. Okay, and then 1 over. Sorry, I think it's invisible, so let me write. Okay, something like this. Then where we have a function, very important function s. So now this sz is a rational function ZQ2, ZQ12 here. So now we have a rational function which depends on both Q and 2. And then a specific thing is that, okay, so this is a rational function. And for example, if you take Q1 or Q2 to one limit, so this just goes to 1. So then that means that if you take, for example, Q2 to one limit, so this just goes back to the Q character. So then in the context of Q character, actually we don't have this S function, but this appearance of this S function is really specific to this QQ character situation. Okay. So then we can discuss several things from this. For example, okay, so this is okay, just a more simplified notation. This is corresponding to this tensor product of this fundamentals of this SL2. And in a usual sense, so we have, okay, so if you know this, I think this gives you this kind of tensor product of decomposition in a usual sense. But okay, how can we see this kind of decomposition in this QQ character? So actually, it's known that okay, even for this Q character, so for generic spectral parameter, actually this tensor product is already irreducible. But if you tune the parameters to x and x prime, so this can be, this is going to be irreducible in a sense that, for example, okay, so for example, this sz function has zeros at, for example, z2 q1 inverse or z q2 inverse. In that sense, if you tune a parameter like this, for example, x prime equal to, for example, q1 inverse here. So then, actually, in this limit, so okay, so let's call this is a star condition. If you apply this star condition, actually this S function gives you 0. So then, under this star condition, actually we only have 3 contributions. This is corresponding to the actually 3-dimensional representation of this SL2. Okay. So this way, so using this QQ character, so we can see how to discuss this kind of decomposition of this tensor product, for example. Okay, this is a one, and yeah. Okay, so okay, in this sense, irreducible means that okay, just considering okay, this is analogous to this. Okay, for example, how to see this decomposition in a classical limit, for example. Yes, and okay, I will come back to this thing later, more geometric sense.
How should I think of this Y? Like what kind of object is this?
Okay, Y is okay. If you want, okay, just a 2-dimensional case. For example, this is a Y plus Y inverse is, of course, this is originally has an interpretation like this. So this is actually basically the Cartan element of SL2, if you want. Yes. Okay, as a group, so this is a Cartan element, but this as a real algebra, this is just a formal thing. But yeah.
If I ask about Y of X, in what class of functions?
Okay, so for the moment, this is a very formal function. Yes, but in the context of gauge theory, so this is going to be, okay, maybe you know. Yes. Yes, so then, okay, yes. Yeah, exactly. So then, yes, Y of X is, okay, in the gauge theory context, this is a generating function of this BPS observable. If you want a 5D. Yeah, at this moment, this is a formal C, yes. But in a more actual gauge theory context, this is going to be the rational function having a pores, etc. But yes. But taking this combination, so this is going to be a nice function, which is a form of regular. Yes. Yeah. So yeah, question here is that okay. So in the context of this Q, okay, quantum affine algebra. So if you think about the tensor product of, for example, this box. So then each box you have parameter x prime. So then in the context of the quantum affine algebra, so this tensor product is not this tensor product itself is already irreducible for generic x prime. But if you tune a parameter like this, so then this tensor product is not irreducible. So then we have a decomposition like this. This is a bit special property of this quantum affine situation. Yeah, generic case, it is, okay, tensor product itself is irreducible, but if you tune a parameter, it's going to be the irreducible, and then we have decomposition, like 2 plus 1, 3 plus 1. Um, yeah, so this is, so this parameter dependence is very crucial, and this is why, so this kind of property is only found in this affine algebra. Okay, if you want, of course, this, okay, so this is representation theory, so we have, for example, sure wide duality, and then we have a kind of symmetric group, and then in this case, this is a bit affinization of this thing. So this, actually, this is, of course, a very crucial algebraic toolkit behind this thing. Yes. Like braiding, etc. But the Q-deformed version. Okay, any question? Okay. Okay, so then this is a bit introduction of this QQ character. And then next, what I want to discuss is, okay, for example, I just give this equation, but for example, how to compute or how to get this kind of tensor product or QQ character in general. Okay, go back to here. So actually, so there basically two descriptions of the QQ character. So one is more, okay, so geometric construction and also algebraic construction of this QQ character. And the geometric construction is more or less like, for example, this Nekrasov in the context of gauge theory. And okay, so just a bit literature information, but this geometric construction, as I will discuss, so we will use the so-called quiver variety or this kind of thing. So then, in that sense, natural realization is only for this AD type. Of course, this SL2 is A1, so then that's fine. But this geometric construction is now will apply only for AD type algebra. But actually, so we have a generalization beyond okay, so beyond AD with Vasily. And in this case, we will introduce a kind of generalization of quiver variety, which reproduces a non-simply less algebra, if you want. Okay, anyways, I will discuss a bit this direction. And another construction is more algebraic construction in the sense that, for example, we can use several, for example, vertex operator construction of this algebra, this QQ character. This is again, this is another joint work with Vasily, but so we can construct this QQ character in the context of the W algebra or its a Q-deformed version, etc. Okay, so anyway, so I'm going to talk about this geometric construction. Okay, so then geometric construction in which sense? For example, this okay, geometric okay, say okay, construction. Okay, so again, let's think about just the SL2 algebra, and then let's think about okay, so tensor product. Okay, again, so we are interested, for example, tensor product in the composition. So let's think about okay, tensor product of this kind of thing. So this is a W times W degree tensor product of fundamental of SL2. Okay, this is again this SL2 fundamental module. So then actually, so it's known that this tensor product has a weight space decomposition that I denote W over V here. So this is just a tensor product, a standard weight space decomposition, which actually each M of W V correspond to the each term in the character in the end. Okay. So then the point here is that for this SL2, actually, so this each weight space M of WV has a very nice geometric realization, which actually use this quiver variety of this type. So then, okay, so it's a very established thing that for SL2, so this is corresponding to the so-called A1 type algebra, and then this has a actual geometric realization as a quiver variety of this A1 quiver. But with now we have so-called framing. So then just removing this framing, so this is just a one node, which is nothing but A1 quiver in this context. Yeah. Okay, in this context, okay, so I will come back to the, more. Yeah, B is now, for example, okay, I think this. Okay, so in this context, so this is a degree 2 tensor product. So then this is corresponding to the W equal 2. And then the first term is B equals 0. And then this is, for example, B equals 1. So we have two terms. And then the last term is corresponding to B equals 2. Sorry, it's a bit difficult to see, yes. But for example, if you have this T, so then tensor product, we have a decomposition, and each term corresponding to this B parameter here. Okay.
But notation is slightly confusing.
Yeah, yes.
At first, you have in the second slot, you have spectral parameter here.
Okay, so for the moment, this is just a standard SL2, then yes. Yes. But in the end, I will add the spectral parameter dependence as well.
The point is the annotation, because you divide it by comma, like before you divided.
Okay, sorry, yes, okay. So then I think, okay. Okay, I see. So this, okay. So in that sense, I think it's better to write, for example, X for the first place, and then maybe, okay, so maybe, sorry, this semicolon to distinguish this dependence. Sorry, yes. So then this is semicolon. Spectral parameter dependence is now semicolon. Okay, and then maybe other question.
Yes. So before you said that this tensor product is generically irreducible, or
Yeah.
it was just the middle part? So is it?
This is in general irreducible.
The whole thing.
Yeah, whole thing. Yes.
So then, if you then identify this sum.
Yeah. So then, so in this case, okay, more precisely speaking, so we have a bunch of the X parameters because so each module we have for example, X1, X2, etc. So then in this case, this is a kind of the set of spectral parameters. Yes, I think this is more correct notation. Sorry. So then, for example, W tensor product, we have W X parameter and the generic W parameter, X parameter. So this is irreducible already. But if you tune a parameter, so it has some decomposition like this.
So when you write it as sum over V, that you mean that it's like sum over modules, or it's?
Yeah, sum over the module. Yeah, if you want. Yeah.
Okay, so then it would be reducible, no?
Sorry.
Or you would assume that already the parameters are special.
Mm-hmm.
Because then you said that you can write it as sum only for special choice of parameters.
Yes.
And here you write it kind of as sum generically.
Yeah, so this is a generic, yes. So then this is, for the moment, let's think of the generic situation. Yes, so generic parameters. Then where we don't have this kind of specialization, etc. Yes.
I don't understand. This is sum of the modules, but in this place, V equals 0 is not a module. It's just one.
Okay, so in that sense, okay. Total thing is, for example, this is a 4-dimensional module. Yes. So then total thing is going to be the module. Okay. Sorry, why? Sorry, which one? B is the eigenvalue of this V. Yeah. So this is of course related to this. For example, if you want, this is related to Y reflection, etc. So then this is of course organized by this root and then Cartan information, of course. Yeah. Okay. Yes.
What is the statement about
Okay. Yeah, I will explain. Yes. Okay. So then, So then, for the moment, we have this kind of quiver, and then especially in this case, we can define quiver variety associated to this thing. So then, let me use a quiver variety. This is carry M, WV here. Okay, I don't give you the precise definition of quiver variety in this case, but in this case, this quiver variety is now given by cotangent of Grassmannian of WB here. So this is a case of quiver variety for A1 case. So then, so in that sense, for example, if you put for example, V cannot be bigger than W. Otherwise, this is going to just empty. So this is related to the finite dimensionless of this module, for example. Okay. So then, let us give you the just kind of proportion. So in terms of this quiver variety, how to express this QQ character. So then this QQ character, okay, let's think about this SL2 case, I mean, A1 case. So let's think about this tensor product of W of this. Okay, it's a bit notation, but we have okay. I think it's better to write 1 n of 1 W. Okay, we have W tensor product. So this has a summation over the B, and then let's use a notation like this. This thing WB X here. So of course this is corresponding to the decomposition with this, and then each contribution can be written as an integral over this Kuiper variety. W. Okay, B W B integral over Kuiper variety. Okay, so then okay, so this character of some okay. Okay, so then this, for example, this epsilon here is so-called universal bundle on this Kuiper variety, and then this y hat is somehow the some certain virtual bundle, formal bundle, which is related to this y function in the end. Okay. And then this integral is interpreted as an equivariant integral. So then this integral is really analogous to the computation of this instanton partial function, if you want. Okay. And okay, so let me discuss several. Let me give several remarks on this formula.
Maybe some simple example of this formula.
Yeah. Okay. So yeah. Okay. So for example, that okay, I will mention that. Okay, I will give the remark here. So which actually, for example, this is an example here. Okay. So sorry. Let me write.
Yeah, what I'm asking is that in this example you have no integrals.
Yeah. So after integral, so this gives you this.
This gives you this as functions, yeah?
Yeah. So then that is related to this y hat. So this y hat is somehow the bundle, and then this character, okay, gives you this y function in the end. So then at the level of this geometric data, so this there's no y function, but a kind of original some underlying bundle here. So then okay. So then, for example, so with this example, so this is a case of this w equal 2. And then each term corresponds to the b equals 0, b1, and the last thing is b equals 2. And actually, so in this example, so for example, we are talking about this w2. So then we have, for example, what is the corresponding Kuiper variety here? In this case, w2, b0, so this is a Grassmannian of 0, 2, but this is just a point. So then just okay, this Grassmannian is just a point, single point. No structure here. But now we have this V1. So this is a Grassmannian 1, 2, which is just a cotangent of P1. If you want, this is a cotangent S2. And the remaining C's, this V of V equal 2 is again this trivial. I mean, just a point. Okay. So then from this point of view, actually this we can understand why we have this S function for this intermediate state. Actually, this S function is actually the contribution of integral over this P1, which is a Kuiper variety of this case. And then in this case, first thing and the third thing, so this is just I mean, Kuiper variety is just a point. So there are no such a specific coefficient here. So then in that sense, and then why you have two contributions for generic parameter is that now we have a considering an equivalent integral. So then we have this, for example, we can apply the equivalent localization to evaluate this integral, which gives you the fixed point contribution, which are just given by this north pole contribution, the south pole contribution. So this is the reason why we have two contributions in the middle case. And yes.
Sorry, question about the notation. What is weight sub Q2?
Okay, so this is, sorry, yes. So this is, first of all, this is a antisymmetric sum of this sum bundle here. And then if you have this, for example, this parameter z, so this is going to be, we have additionally this kind of twist parameter. Yes. So then if you take Q2 1, so this is just reduced to the standard antisymmetric sum. And then, but this has a bit twisted antisymmetric sum.
I mean, in the first line, you don't have any Q2. So,
yeah, first line, yeah, we don't have Q2. Yeah.
but second line, you make a twist.
Yeah, with respect to Q2. Yeah, so this is integral of, integrand is from here to here. Yes. And from this point of view, okay, so for example, this example, basically two Q parameters, Q1, Q2 are basically equal footing, but this formula, it's not. So, but this is somehow the non-trivial thing, and if you, okay, so of course we can, Q1 is actually the, appeared as an equivalent parameter here. So then, okay, Q1 dependency is actually a bit hidden in this definition of this integral. But
I mean, in that expression, Q1, Q2.
Yeah, equal footing. Yes, yes. In the end, so this is a bit non-trivial point, but yeah, from this expression, yeah, it's not clear how this Q1, Q2 are symmetric. Okay, so then if you want, you can apply this equivalent integral, and then so we can apply both Q1, Q2 as an equivalent parameter, which is related to the group action of this on a vector space related to this equivality. And then the computation is really analogous to this instanton Partition function, so which has Q1, Q2 actually. Yes. I will come to the next example, which is more close to instanton Partition function.
And x's are invariant ways of the non-double, right?
Yes, yes, yes. So then in this case, this x is interpreted equivalent parameter associated to this w here. Yes.
Can you just show computation for a case v equal 1, so most of the terms vanish on the right?
Yeah, so this v equals 1 is just a kind of one variable integral.
Yeah, but I guess in this case it's very easy to compute integral.
Yeah, so this is the integral over just equivalent integral of P1. So then we have only two contributions which correspond to north pole, south pole, which are fixed point under this.
V equals 1, you say that there is a point, it's not P1.
V equal 1 is a TP1. Yeah. V equals this is a point. So then just I mean no this thing, but this is a kind of external source, and then this only this contribution survives, and then this gives you the basically this y contribution. If you want. Y hat is somehow the okay in the context of this geometric realization. So we have several the kind of the formal bundle, which is going to be related to this y function. So basically, this character of this y hat is now converted to the y function in the end. Yes. Okay, so then, okay, in the context of, for example, so this is again a universal bundle of other instanton modular space, etc. But just to define the QQ character, so this is just a formal bundle here. Yeah, so yeah, yes, equivalent localization, yes, something like this. Yes, additional contribution. Yes, exactly. Yes. Yeah, exactly. So technologically, so it's really similar, but we have additional insertion. Sorry, which one? Y hat. So then, okay, this is more or less okay. So in the content, okay, so if you are just interested in instanton partition function, we don't have this, but this corresponds to the situation in the present. Okay, the instanton partition function in the presence of, for example, Wilson loop or something like this. Actually, so this is going to be this is related to the previous question, but this QQ character is going to be the okay in the 5D setups. This is going to be the generative function of Wilson loop along this additional S1 or something like this, chiral ring operator. So that's why we have additional insertion. Okay. Any other function. Okay, so then, okay, quick remark is that, okay, so again, this is related to this question. Of course, for example, the naively, so what happens if you don't have this additional insertion? In this case, this formula is exactly same as the so-called Hirschi-Wolff chi-y genus, but the y parameter is now Q2. So then this is actually generalization. Okay, this is a bit additional, chi-y genus in the presence of this additional insertion. And okay, so this is one one thing. And then actually this I don't know about the motivation, but the chi-y genus is interpreted as kind of a modification of Euler characteristics. So then in this context, if you take just Q2 to 1 limits, so this is more or less reduced to the computation of Euler characteristics, something like this. So then in that sense, we have originally just a several generalization, modification of Euler characteristics of this quiver variety. So this actually is used to compute the QQ character in this context. Okay. Okay, so then this is one example. But of course, this once you have this geometric data, so we can think about more generic situation. So this is just SL2, but okay, remaining time. So let's discuss more generic situation. Yes, in this case, yeah, this is a definition, yes. And then we can see for this definition is how this is compatible with other definition or. Yeah, so then proposition is that, okay, so QQ character, okay, there are several, okay, for example, this algebraic construction, etc. And then using this geometric integral, so this actually coincides with the other definition of, for example, QQ character and so on. Yeah. So this is a statement here. Okay. Okay, so then this is first maybe the non-trivial example. And the next example is that, so this okay, so for the moment we have discussed SL2 or it's a quantum affine SL2, but actually same technology can be applied for this so-called quantum toroidal algebra, which is one more affinization. And let's denote this as, for example, algebra E. So this is a kind of the traditional way to describe this quantum toroidal GL1. And this also has another name like the Dino-Haramiki algebra or elliptic homology algebra, etc. But anyway, so let's think about this. And what is, for example, quiver variety corresponding to this is following. So correspondingly, so we have actually, so we have, so this is again the rank 1. So we have again single node here, but now we have actually edge loop, loop edge here. So in that sense, okay, so if you want, you can write this as double arrow notation, but anyway, so existence of this additional arrow is of course different from the previous example. And then this quiver.
W was the degree of the real product of representation.
Yes, yes.
Now you do like the same.
Yeah. So then the W is fixed, and then we will have a summation over the B. B called.
What kind of representation do you
Okay, so I will mention, but this is for the moment Fock module of this. Yes. And I want to discuss more also for the McMahon module, but anyway. Okay, so then in this case, this quiver is called somehow this A0 hat quiver, or as the name is I think Jordan quiver. Okay. Of course, this is actually the first example of this affine type quiver. So then we have it slight difference, but actually we can compute, we can apply the same methodology to realize this QQ character of this quantum toroidal GL1. Okay. And then actually, so yeah, this is rectification, but in this case we have, okay, so this quantum toroidal algebra, we have this E module. So we have, it's known that there are 3 module, vector module, and Fock, and then McMahon. So we have, it's known that this quantum toroidal GL1 have 3 modules. And then how to parameterize this is that, okay, so actually this vector representation module is labeled by actually the one-dimensional partition. And the fork module is now then, parameterized by this partition, 2D partition. And actually, so this, yes. And then the McMahon module is, actually, this is so this three-dimensional partition nicely parameterizes this McMahon module. So then in this context, in the context of instant counting, so this is kind of the vortex partition function. Fork is related to instanton counting, and then McMahon is a kind of D0, D6 brain type system.
It's like by integers or also negative, sorry, positive integers?
In this case, yeah, both positive and negative. Yes, yes. Yes, this is a bit a tricky point, but yes. And actually, so so this case we can apply the same methodology, but in this case, we can discuss this fork module of this quantum controller GL1 using this technology. So in that sense, just a quiver variety associated this Jordan quiver. So then we can compute the QQ character of this fork module of this quantum controller GL1.
Are you going to do a geometric construction?
Okay, so
Algebraic.
so using quiver variety, this is a geometric construction. And then if you want, we can apply the algebraic construction, which uses a kind of one more optimization of double algebra, actually. Yes, yeah. That I cannot talk in this talk, but okay. So then, for example, let's think about a QQ character. Okay, so let's call this fork module. Fork module of, for example, again we have a spectral parameter here, then f of x, and the McMahon. Okay, this is for example vector of x, and the McMahon of x. So let's denote this, and let's think about a fork module which depends on the parameter x here. And then if you want to, you can, in general, think about the tensor product of these representations. So this fork, QQ character fork module of this quantum controller GL1 takes a form like this. Again, we have y. So let me use this notation. Okay, maybe this. Plus. Okay, I just only write first two terms. But the reason why is that now, previously, so we have discussed SL2. But in this case, this is discuss a finite dimensional module. So then we have just, for example, 4 terms here. But in this fork module is these 3 modules are actually, all of them are infinite dimensional. So then the corresponding character is actually going to be the infinite series. Okay, so this is one very important property here. And then what is this parameter here? Q3, Q4. So now,
Each term corresponds to some Young diagram.
yeah, okay, yes. For example, this case we have, so I will come back to this, yes. Okay, so then, step by step. So now we have Q3, Q4 parameter. It's a kind of additional parameter. And, if you want, this is related to the kind of adjoint mass with respect to this edge loop. But now, we have a parameter. Okay, originally we have Q1, Q2 for the QQ character. But now we have Q2, Q3, Q4 equal to 1 condition. So then, in that sense, we already have Q1, Q2, but additionally Q3, for example, appearing here. But Q4 is automatically fixed by this condition, which is actually this CY4 condition, if you want. So then, actually, in this QQ character of this quantum controller, so we have kind of underlying structure is actually the Calabian fourfold. And then, so then, related to the question, and then,
How this you are related to center of charges or center of tension?
yeah, exactly, yeah. Yes, so, okay, I will come back to, yes, I will explain soon. Okay, so then, this is an infinite sum, but the infinite sum is nicely organized, by this, lambda, which is actually partition. So as I mentioned, this fork module is nicely parameterized by this, 2D partition. So then, we have, so for example, this, of Q1, 2, 3, 4, Q parameters, and also this X parameter here. Then we have certain Okay, so for example, I just formally write this. For example, this z is a kind of the rational function in terms of this q1, q2, q1 to 4 parameter, which is corresponding, for example, s part. And the y of lambda is just a simplified notation of, for example, combination of this, just a product of this y functions. Okay. So then, so then actually, for example, this case is corresponding to the Young diagram, partition empty. And these contributions, first one is corresponding to the Young diagram with a single box. And the next thing is, okay, I don't write, but we have two options like this. This is a 2-box contribution, something like this. And actually, so, okay, so just looking at the geometric origin of this z function, actually this is nothing but, okay, in this context, so this u1, the 5D necklace of function of, okay, but this is actually n equal 1-star theory. This z is actually exactly same as this 5D necklace of function of u1 here. This is okay. Okay, so we have q1, q2 is a standard parameters. I mean, background. q3 is actually the adjoint mass parameter here. Yes, and the q4 is automatically fixed by this. Yes. So then, okay, recording the original, realization of this geometric, realization of this. So this is, okay, in this case, this integral is nothing but the integral over this quiver variety associated this. So this is nothing but the ADHM moduli space in this context, or Hilbert scheme. So that's why, so we have this z function as a necklace function. But now we have a specific additional contribution, which is a bit different. Okay. So in that sense, this is something. Okay, so yes, for example, okay, in general, okay, so then for this purpose, I think it's better to think about what will be changed if you change this quiver structure. So this is so-called, Makai-Nakajima correspondence, in the sense that if you think about this kind of quotient space, so then corresponding modular space is organized by this, for example, okay, this bit abuse the notation, but if you think about, for example, Z-type, okay, A-type singularity, we have corresponding modular space is actually affinization of this, for example, affine A-type quiver, for example. Then actually, if you think about A equal A0, which is just a quotient by just a trivial thing, so this is corresponding to this quiver. So that's why, yeah, so this is one reason here. Okay. So then,
this y lambda is constructed by this addable and removable.
Yeah, exactly. Yes, yes. So this depends on, okay, so we have the bunch of the product, but this is nice organized by this shape of this Young diagram. Okay. Any question? Okay. So then, okay, so actually this formulation still works for this infinite dimensional case. And then, okay, so we have several questions. So then, for example, this is okay. This is fine. But the next question is, the natural question is that okay. So now Fock module is fine. Okay, vector is more or less a deduction from this Fock to vector. Okay, it's a bit subtlety, but okay. So then the next question is what? Okay, is it really similarly possible to realize somehow QQ character of magma home module? So this is the next question. So then, okay, I just give you the formula. Geometric formula for this magma home module. So then, QQ character of this magma home module. Okay, sorry, this is okay. Let's say this is a bold n for this magma home module. Sorry for notation. Bold n, which is again having a parameter x. And actually, so this has similarly decomposition over this v. And then this is a QQ character of this M of. Okay, I'll explain. Yes, this is going to be the degree of the Hilbert scheme of C3, but okay, number of instanton. I will explain that. Okay, so for example, this. Okay, so, okay, so if you want, this is decomposed as V with, yeah. So this kind of say, canonical ensemble or grand canonical ensemble expression. So then, so to have a geometric realization, it's better to think like this, so canonical ensemble. Okay, so then, so then we have, for example, B of X. So then we have this QQ character of this each contribution has a geometric realization. This is the integral over this so-called Hilbert scheme of points of C3. With again similarly have this insertion of this universal bundle and so on. Okay, this is a tangent of X here. Okay, where? So it looks very similar to the previous case, but the difference here is that actually no insertion of this Q2 shift here. And then, this integral. This is a so this this M is a McMahon. V is a number of the boxes in this plane partition. Yes, yes. So this is sum over. Okay. If you want, this is again given by the sum over the plane partition. But now, in order to have this geometric realization, we have kind of fixed number of boxes and then rearrange the summation here. Okay, the first part is essentially the same. So this E is again universal bundle over the Hilbert scheme. Then Y is similarly some kind of the formal bundle, which is related to Y function. And then now we only have this total class here, and we don't have a Q2 twist. So this is this is more or less for the moment it's a bit heuristic thing, but actually this reproduces a QQ character, which is obtained by another computation, which is more with instanton counting like thing, etc. And then so one of the reasons why is that so for the standard quiver variety. So then, for example, we have a finite dimension is finite, but the Hilbert scheme of C3, actually, for example, virtual dimension is going to be 0. So then we don't have any further insertion. This is a bit technical explanation, but okay. So, anyway, so then in the end, so this is going to be the summation over the plane partition. Okay, that's fine. Okay, so then, so then we have this kind of Fock module, etc., QQ character, but then, so what is some advantage to think about this, any application or especially this physical application of this technology, or this QQ character constructed here. Okay. So one possible connection is actually.
Can you compute that integral explicitly?
Yeah, this is an equivalent integral, yes.
And you can compute it explicitly.
Yeah, so then this is again reduced to the Cantor integral formula. Then just pick up all the residues, and then the fixed point is nicely parameterized by again this plane partition here. Yes. Yes. So, technical point is history is very similar to standard instanton modular space integral. Okay. Number of the points in C3. Yes. Yeah, this is yes. And then after that, so we will take a summation over all the possible b equals 0 to infinity. Okay, so then application. So then just come back to the original motivation of, for example, Q character of the, for example, Frankel-Reshetty. So one of their motivation is that actually this Q character has a nice interpretation in terms of the quantum integral system. And actually, so we have a QQ character. And then this is reduced to the, for example, take Q2 to 1 limit. So this is going to be the Q character. And in the physics, instanton counting context, this is nothing but a Nekrasov-Shatasvili limit. So in the sense that it's really reasonable that if in this limit we can make some connection with a quantum integral system. Yes. Yes. Yeah, bold face. Yes, McMahon. Okay. So, sorry. Yes. Sorry. Sorry. This is sorry. This is a tangent of a Hilbert scheme. Sorry. Yeah. Sorry. This is okay. So it's a bit difficult. Okay. So if you write this as so carry n of in this case this corresponds to the W equal 1, but B. So then this is going to be the tangent of Hilbert scheme of degree V. Yes. Yeah, thank you for this pointed out. And then, okay, the short, quick mention is that this is corresponding to rank 1, but we can similarly think about a higher rank generalization, which is geometrically realized as a COT scheme of this C3. But this is corresponding to the, for example, higher rank generalization of Donaldson-Thomas engine. Okay, so anyway, so then just finally, last 5 minutes, I mentioned some application of this technology. So again, so this QQ character is a, situation with a generic Q1, Q2. So if you take a Q1 to 1, okay, for example, if you want to, you can also take Q1 to 1, but so if you take this limit, so this QQ character leads to Q character, but this is nothing but a Nekrasov-Shatashev limit, which gives you some connection to the quantum integral of the system. So actually, for example, from this point of view, actually QQ character that we constructed, but already, for example, this Q character of this E algebra, E module. So this is okay. This quantum toroidal GL1. This is was already given by this Feigin-Jimbo-Miang thing, both for this Fock and McMahon module. So then one thing is that of course we can check deduction from this QQ character, this Q character. But of course this is almost very straightforward. And then and actually one of the reasons why these people study this Q character in this quantum toroidal is that some potentially new quantum integral system. And actually, so we can consider we can derive the Bethe equation associated to this quantum toroidal algebra. Associated, okay, for is this Fock module here. So this was, okay, so this Bethe equation for this Fock module was given by this Feigin-Jimbo-Miang thinking. And let's just write what is a Bethe equation here. So this, we have several notation, but now we have this Q3 x of Q3 here. And then where this Q of x is a so-called Baxter Q function, which is a polynomial function in gen. Okay, so formally, okay, so this is I of x minus. Okay, it's a bit, okay, multiplicative notation, so it's going to be the sign hyperbolic, but okay, I think no confusion. Okay, yeah. Yes, 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 yes. This is 1, yes. Otherwise, we have a bit coefficient, but basically you have just a x independent part, and then this is going to be this. And then now we have this limit. So then in this Nekrasov-Shatashev type limit, we have Q1, Q3, Q4 is going to be 1. So this is a more standard condition for the quantum toroidal algebra. We have 3 parameters having this kind of condition. And okay, so precisely speaking, this is going to be a sign hyperbolic, but x minus x. In a 5D multiplicative notation. And actually, so this behaves like okay, x to infinity. This behaves like a gamma function. Of if you want, this is a Q gamma function. Okay, so actually, so this kind of generalized version of Bethe equation was discussed in several contexts. Maybe Thomas will mention this Bethe equation this afternoon. But okay, so this is known for this Fock module. Then a question is, okay, so is it possible to do the similar computation equal McMahon module here? Actually, okay, so let's think of this equation. Okay, this is actually same Bethe equation. So we can get the same equation because we have the same algebra. So then we have the same Bethe equation, but the representation is different. But actually, this Q character, Q function is going to be a bit different behavior in a sense that, okay, this IJ, and this behaves like, okay, Q, Okay, so let me use this kind of, this is a Q analog of this double gamma function. So actually this, distribution of beta roots is a bit different for this Markman-Horn module, but the still beta equation is, although we have the same beta equation, but actually this asymptote behavior or this distribution of beta roots are a bit different for this Markman-Horn module. And the reason, okay, so then the reason why we have this double gamma function is following. For example, in the context of this relation between integrable system and gauge theory, we have a natural realization as a codimension 2 surface defect. But in this case, okay, so for example, we have the C inside of C2. So this is actually mostly corresponding to the first realization. But now this Markman-Horn module is associated to the C3 instanton counting. So in that case, actually, okay, so this is for more or less this fork. Actually, in this case, C2 Markman-Horn, actually. So,
But in the first slide, there should be also the circle, no? Because you have the hyperbolic side. So, are you sure it is C or
sorry,
is
which,
inside to the circle?
sorry, which one?
The first, because, yes.
This one?
Yeah. Because there you have the hyperbolic side, no?
Yeah, this is hyperbolic sign. So then asymptotic behavior of this Q function is going to be the Q gamma function. Yeah.
So you're considering the, for the Q gamma function, is the C inside C2.
Yes. So then, okay. So originally the setup is a kind of the real 4D kind of instant partition function. And then in order to make a connection with the quantum integral system, so we typically insert a surface defect, which is a C inside C2. So then, for example, typically this, for example, vortex partition function asymptotic behavior is given by gamma function, for example. Okay.
No, but the Q gamma function is for C.
Okay, yeah, yes, yeah, if you want, yeah, precisely speaking, yeah, we have additional S1 direction. Yes, yeah, sorry, yes.
Okay.
Yeah, of course we can just think about reduced situation, but anyway. Yes. So then, okay, so then the analogy here is that now, okay, so this is not yet explicitly examined, but this situation, Markman-Horn module, so the corresponding defect is actually real 4 dimensions. And actually real 4-dimensional partition function gives you the double gamma type contribution. So that's why we have a bit different kind of distribution. So then, okay, so explicit construction of wave function, etc., is not yet done, but this is this is implication from this QQ character construction and something like this. Okay, so then I think it's nice to stop here, and thank you for your attention.
Thank you very much for a nice talk. Any questions?
Why is the example of this n equals 2 star in partition function and not pure gauge theory?
Okay, yeah, of course, if you want, you can think about the pure gauge analog of this QQ character, but actually this behavior is not so much good. So then, yeah, so then this is just a bit technical reason why we start with n equal 2 star. Yeah, as a algebraic point of view, if you think about the pure sync, so we will have a shifted quantum affine or shifted quantum toroid algebra, which is a bit involved than the standard one.
What's the interpretation of those functions in which
Here, yes. So then, so you mean Q function? Yes. So this is roughly the partition function of the defect in this setup. For example, this first situation, so this is originally real 4D, but if you impose a real 2D object, so then this Q function is more or less interpreted as a partition function contribution of this defect part, roughly.
normally those functions they have some kind of orthogonality condition. Let's say.
Yes, in the context of integral system, yes.
Yeah, but
yes.
what's the meaning kind of orthogonality condition?
Yes. So yeah, so at this moment, so okay, so for the moment we have just derived beta equation, and we don't yet examine so more detailed property here. So then at this moment, honestly speaking, I don't yet establish this kind of thing, especially for this. This is more or less established for the standard integral system, but this is a bit more general thing. For example, if you think about distribution is different, so corresponding, for example, TBA equation, etc., it should be modified corresponding. In this sense, okay, I don't know, especially for what happened with this. Maybe. Okay.
The first one is about, you mentioned briefly that there is a high advanced version
Yes, higher rank version of this. Yes. Okay, so higher rank means that, okay, I just erased for the fork module case. In this case, partition function is a U1 recursive function. But in order to get the higher rank recursive partition function, you should think about the tensor product of fork module, etc. So this case, we have a similar interpretation, like this is a U1 partition function of 60. But if you think about higher rank thing, so you should think about tensor product of this Hilbert scheme. So this is going to be the so-called fourth scheme instead of the Hilbert scheme. So this is analogous to the people.
Another question was related to the format you erased.
Yeah.
Because you were saying that you have a sum over characters where you had a contribution which was the U1 by the class.
Yes.
But that contribution was labeled by a partition.
Partition, yes.
And you were multiplying that partition with some other quantity, which was a generalization or a product of Y gas.
Yes.
So the necessary partition function for U1 would be the sum over the partition of that expression without the Y.
Yeah, so Y to be, for example, 1, it just gives you the necross.
Y have a physical interpretation, the addition of Y.
Yes, additional Y in this context is that, okay, for example, 5D case, this is a contribution of additional Wilson loop along this S1 direction. Configuration, okay, instant on background, actually. Okay, yes.
So where is that label in your
Okay, so in this case, this is actually the fundamental. So if you want, you can think about, tensor product, etc. Yeah.
But there are other decorations corresponding to other representations.
Yes.
Like by lines in different representations.
Yeah. So we have several representations, so that it's a bit confusing, but yes.
Because then, like, if that's the case, then it's natural to expect that if you start using.
Yeah. Sure. Yes.
Representations, then they will respect the blacklisms of the.
Yeah. Sure. Yes. Yeah.
Is that also presented by the partition functions of the computer?
Yeah. Basically, so we can do the higher representation, and in that case, of course, we have more involved computation, but we have several interaction between Wilson loop also, and of course, if you think about the fusion limit, etc., yeah, we have a much structure actually. Yes.
Other questions? Comments? Okay. Now, let's thank the speaker again.
Thank you very much.